Okay, we finished off last time talking a little bit about the triggers for star formation. We said molecular clouds could collide together and increase the density. We said that new stars could turn on, and that can cause a radiation pressure that can increase the density of a molecular cloud to such an extent that gravity takes over and starts making it collapse. Or we could have a supernova. A supernova is a massive star that's nearing the end of its life, and we're going to be talking about it a lot in the next couple chapters. It basically goes out with a bang, it explodes, and as it does, it goes out very violently and it makes a shock wave. And that shock wave in this artist's rendition will increase the density of this cloud as it passes by, and that triggers the collapse of little nodules within this cloud that will then turn into new stars. So it's a fascinating thing because basically the death of one star produces the birth of many, many, many more. So here's the animation. It's a very, very short one. Okay, you see the supernova exploding, the shock wave comes out, and that increases the density of the molecular cloud. Causes, of course, is in very fast motion. It doesn't happen this quickly. But that shows you how, in essence, a supernova can actually increase the possibility of new star formation. Okay, and acts like a trigger of star formation. Okay, so we finished up last time talking about all these different triggers of star formation. And so now let's just talk about a little bit of the characteristics of star formation. Okay, so what you get once the cloud starts collapsing, it will fragment into smaller clumps. It won't collapse into one gigantic, enormous star. Generally, it'll contract into clumps. These clumps will get hot as they contract because gravitational energy turns into heat. Whenever you drop something on the ground, for example, the thing that you've dropped and also the ground will heat up slightly, turning that gravitational energy into heat. The same thing is true when material gets pulled together by gravity. Some of that gravitational energy goes up and goes into heating that object. And what ends up happening is you get what's called a protostar. A protostar is a star that's not quite a star yet. It's a clump of gas that's getting denser and denser and hotter, but it's not hot enough to produce its own energy by nuclear fusion. It's producing its own energy by its gravitational collapse, but it's not shining by nuclear fusion. It's not a true star yet. Okay, it's on its way to becoming a star. Okay, here is a very famous photo. This was dubbed the Pillars of Creation because they look like pillars, although they're shown sideways here. Well, there's no up and down in space, but basically this is a small part of something called the Eagle Nebula. The Eagle Nebula is named so because if you have a good imagination, it looks a little bit like an eagle with the wings here, and then sort of the talons of the eagle's legs would be down here, and those are the pillars we're talking about. At any rate, when the Hubble telescope saw these pillars of creation, they found that there were little tiny new stars coming out. These are bits of the giant molecular cloud, and these parts of the cloud were enhanced in density because of very, very hot stars somewhere out here, shining upon them and making them denser and denser, and eventually gravity pulls them together to make brand new stars. You can see some of the stars emerging from the pillars right here and here and here, and others coming out of these little sort of fingers from the star, from the pillars. Okay, so new stars forming happens within these emission nebula, which are just portions of the giant molecular cloud. You can see the dark pillars there, which are very, very dense, part of the original dense dust and gas clouds. And the bright new stars that have already formed are enhancing the formation of these young stars. Okay. Now, when these protostars collapse further and become hot enough on the inside to reach about 10 million degrees, Then the contraction stops because nuclear fusion begins. Okay, we're going to talk in detail about nuclear fusion. Those of you who had Astro 1, we talked about nuclear fusion and how it relates to the sun's energy. Basically, all stars shine by nuclear fusion, although the processes are not exactly the same for every star. When that occurs, it's called a zero-age main sequence star. Okay, a main sequence star is a star that's in the prime of its life. In this case, it's a brand new prime of life star. Okay, zero age means it's just starting its prime of its life. Okay. All right. So some characteristics of star formation. Sorry, that's not on the. Get that in there. Okay, some characteristics of star formation. Again, we have an emission nebula here. We have a cluster of young stars that have formed, and they've sort of eaten away kind of a donut hole in the center of this nebula. You can see these hot, bright blue stars are probably very, very massive. Okay, these are called OB associations. Okay, these groups of bright, hot young stars are generally found near molecular clouds. Whenever a molecular cloud starts to collapse in a place, you get a smattering, a handful of these really hot, bright stars. And these really hot, bright stars are what causes the surrounding gas to heat up and glow. So without these hot, bright stars, we wouldn't be able to see this gas out here. We wouldn't have an emission nebula. Also, without these hot, bright stars, there would be probably less star formation in the surrounding nebula. It eats away at some of the nebula, but it also condenses the region around it, and that makes the gravity pull itself together, pull the clumps together even more strongly, making a lot of new stars. Okay. When the gases out here recapture the electrons, they cascade down, the electrons cascade down through the energy levels, making the bright spectral lines that we talked about back in chapter 6. Okay. In addition to being called emission nebula, these things are also called H2 regions. Okay. H Roman numeral 2. Okay, they're called H2 regions because neutral hydrogen is called H Roman numeral 1. Unfortunately, when you say it, you can't tell the difference between H2 and H2 with a little subscript 2. This is molecular hydrogen. This is what's in the molecular cloud when you have two hydrogen atoms bound together in a sort of baton-shaped molecule. Okay, that's not the same as this H2. This H2 is basically hydrogen that's nothing but free protons and free electrons flying around all by themselves. Okay, so it's ionized hydrogen. Totally different. I mean, it's the same substance, but in a different configuration. So this is so hot, the H2 is so hot that the electrons have been ripped off from the protons and they're both flying around separately. Okay. Now, the star's radiation pressure, okay, as I said, often compresses the surrounding gas and dust right around here. Okay, so the radiation pressure from these young stars compresses this gas and dust, often making more protostars form, kind of like a chain reaction. All right. Now, you would think that the bigger the star is, the more massive a star is, the longer it would take to form. But that turns out to be exactly the opposite. Okay, these hot, bright blue stars tend to form very, very quickly because they have more mass. Because remember, the force of gravity depends directly on the mass. And if there's more mass, there's going to be more force, and there's going to be more force pulling the material together. It's going to fall together much more quickly. And so a massive star takes a much shorter time to form than a low mass star. Okay? So more massive protostars form faster because their gravity is stronger. Here's a diagram, an HR diagram, with luminosity on the vertical axis and temperature on the horizontal axis. And again, the main sequence along here is, this is the zero age main sequence line. This is where the stars become real stars. Okay, and I'm not sure how helpful this is to you, but these lines here are lines of equal amounts of time. So, for example, what this is saying is that a 15 solar mass star will come together to make a normal star in only about 10 to the 5th years. 10 to the 5th years is 100,000 years. That sounds like a long time to you and me, but to a star, that's a very, very short time. So a 15 solar mass star takes a very short time to come together to make a star. So that would be like those bright blue stars I showed you in the picture on the previous page. Okay, a 5 solar mass star comes together. It's near this dotted line here, which is 1,000,000 years, 10 to the 6th years. So this takes 1,000,000 years to come together. That's more than 100,000, but it's only 10 times as much as 100,000. 1,000,000 years is still a very short period of time for a star. Okay, a 2 solar mass star will take around 10 million years to come together. Again, that's not all that long. Our sun probably took maybe 20, 30, 40 million years for it to come together. Okay, so basically, more massive stars take very, very short periods of time to come together. That's what you want to take away from this. A 30 solar mass star might take only 30,000 years to form, whereas a really low mass star, like a 1/5 solar mass star, a star that has only 1/5 of the mass of our sun, will take 1 billion years to form. The really amazing thing about that is that's longer than these stars even last once they do form. So it takes longer for these stars to actually form than it takes these stars to carry on their entire lives. Okay, so these are the trends you have to understand. Massive stars form quickly, but they also live their lives quickly and they die quickly. All right. Oftentimes when you see newborn stars, well, actually, oftentimes you can't see newborn stars, all right, because they tend to form in these dusty environments, and as you know, dust tends to obscure your view of things. Okay, these are 2 pictures of exactly the same region in space. Okay, this is a Mission Nebula, and you see kind of a dark, dusty cloud here. This is an obscuration or a dark nebula. But with infrared light, with an infrared telescope, this is the part that glows. You can see that the dark part here has lots and lots of hot dust, and it also has a lot of bright new protostars, brand new stars that are still surrounded by these dusty cocoons from their original birth. Okay, so oftentimes you'll see brand new stars surrounded by these dust clouds, and these dust clouds are warmed to several hundred degrees, and they emit infrared light, so you're able to see these dust clouds surrounding the protostars in infrared light. Okay, and let me just go real quickly on the last page of notes here. So basically, you can identify star-forming regions by a bunch of different things, which we've all really talked about already. You can find these clouds of gas and dust illuminated by a cluster of stars. Some of the gas will be ionized, and the dust will sometimes be reflecting the light from the embedded stars within. You'll get a lot of hot blue O and B stars. Okay, the reason you tend to see O and B stars there is because they just don't live long enough to wander away from where they were born. And so when you see lots of O and B stars, that tends to be places where stars are forming. If you see, like we saw on the previous page, clusters of stars and nebula that are visible only in the infrared, well, that's a dead giveaway of star formation as well, because these brand new stars are still surrounded by their dusty cocoons. And then, as we said, stars tend to be born in clusters, siblings. This is the famous Pleiades cluster. And you can see this cluster of stars with your naked eye on a night in the midwinter. It's in the constellation of Taurus. This is called an open or galactic cluster, and you can still see some of the leftover dust from the formation of these stars, the Seven Sisters as they're called. Okay, so that is basically what we're going to talk about, all we're going to talk about with star formation.